You have learned that the entire positive charge and most of the mass of an atom is concentrated at its center, which is referred to as the nucleus. Generally, mass of a substance is measured in kilogram, but in the atomic sense, this is a very, very big unit. Hence, atomic mass and also the mass of its constituents is measured in atomic mass unit denoted by AMU or U. Atomic mass unit U is defined as 1/12 of the mass of a carbon-12 atom. Mass of a carbon-12 atom is 1.992647 into 10 power minus 26 kilogram. Thus, one atomic mass unit is approximately equal to 1.66 into 10 power minus 27 kilogram. A mass spectrometer is used to measure atomic mass accurately. This involves considering the various isotopes of an element. Let us first learn about isotopes of an element. Elements available naturally may be composed of atoms having the same number of protons but a different number of neutrons. Thus, we have atoms of the same element having different mass numbers or atomic masses. Such atoms are referred to as isotopes of the element. The isotopes of a given element occupy the same place in the periodic table as they all have the same atomic number. However, they may differ in their nuclear properties. Among the various isotopes of a given element, some may be more abundant than others. The percentage of a particular isotope of an element found in the nature is known as its relative abundance. Practically, every element consists of a mixture of isotopes. For example, the lightest element, hydrogen, has 3 isotopes, namely protium or hydrogen, deuterium and tritium, having masses 1.0078 AMU, 2.0141 AMU and 3.0160 AMU respectively. Of these, the lightest isotope has a relative abundance of 99.985% and its nucleus is called the proton. The average mass of an atom or atomic mass is obtained by the weighted average of the masses of its different isotopes. For example, the atomic mass of hydrogen is the weighted average of the masses of protium and deuterium, the 2 natural isotopes of hydrogen. The relative abundance of protium is 99.985% and that of deuterium is 0.015% and their atomic weights are 1.0078 AMU and 2.0141 AMU respectively. And knowing these values, we calculate the atomic mass of hydrogen and it is found to be equal to 1.00783 AMU. The nucleus is positively charged because of the constituent protons. A proton carries 1 unit of fundamental charge, E, and is stable. The total charge on the electrons in an atom having an atomic number Z will be equal to minus Ze, since each electron carries a charge minus E. As every atom is on the whole electrically neutral, it should have a Ze positive charge. This makes it clear that the nucleus has Z protons. If we assume that the electrons and protons are the only constituents of the nucleus, then the atomic mass should be equal to the sum of the masses of protons and the electrons of the atom. For example, hydrogen has 3 isotopes whose atomic masses are 1.0078 AMU, 2.0141 AMU, and 3.0160 AMU atomic mass units respectively. If we look at hydrogen, its atomic mass is exactly equal to the sum of the masses of the proton and the electron in it. Hence, the difference between the atomic mass and sum of the masses of the protons and the electrons is equal to 0. But in the case of deuterium and tritium, this difference is not equal to 0. This indicates that apart from protons and electrons, there are other particles present in the atom. Now let us look at the experiment conducted by Chadwick that led to the discovery of the unknown particles that were existing in the nucleus along with the proton. Chadwick's experimental setup consisted of a polonium source, which emitted alpha particles towards a beryllium target. The particles emitted from beryllium were found to have carbon nuclei along with some neutral particles. The neutrality of these emitted particles was tested by passing them through the region between the charged plates of a capacitor, where they were found to be neutral. These emitted neutral particles are made to fall on paraffin wax. The particles resulting from paraffin wax are hydrogen nuclei, which are nothing but protons. These protons are made to enter a cloud chamber where they ionize the gas present, resulting in an ionization current that can be detected by a galvanometer when the current flows in the external circuit. Initially, it was assumed that the neutral particles emitted were photons. But the neutral particles were able to knock off protons from the paraffin wax. Studies showed that to knock off a photon should possess huge energy. But the neutral particles observed in the experiment possessed much lesser energies. Yet, they were able to knock off the protons from the paraffin wax. Therefore, Chadwick assumed that these neutral particles were of the same mass as that of the protons. Calculations done on the basis of this assumption by applying the law of conservation of energy and momentum showed this assumption was in excellent agreement with the results obtained experimentally. The nuclear reaction occurring in Chadwick's experiment can be summarized as 2He4 plus 4Be9 gives 6C12 plus 0N1. Here, 0N1 represents the neutron. Thus, a neutron is a neutral particle having a mass nearly equal to that of a proton, which is equal to 1.00866 AMU or 1.6749 into 10 power minus 27 kilogram. A free neutron is unstable, just like a proton, and has a mean life of about 1000 seconds. A free neutron decays into a proton, electron, and an antineutrino. Therefore, the nucleus consists of positively charged protons and neutral neutrons. Neutrons and protons together are called nucleons. The total number of nucleons in a nucleus is called the atomic mass number and is denoted by A. The total number of protons in a nucleus is called the atomic number and is denoted by Z. The total number of neutrons in a nucleus is called the neutron number and is denoted by N. In the notation for the nuclear species or nuclides, X is the chemical symbol of the element, A is its atomic mass, and Z is its atomic number. For example, in the nucleus of carbon-14, the notation for the nuclide conveys the information that this carbon nuclide contains 14 nucleons, 6 protons, and 14 minus 6 equals 8 neutrons. Isotopes are nuclides of the same element, but with different mass numbers. For example, carbon-12, carbon-14 are said to be isotopes of the carbon nucleus. Similarly, H1, H2, and H3 are said to be the isotopes of the hydrogen nuclide. H2 is referred to as deuterium and H3 is referred to as tritium. The deuterium nucleus has 1 proton and 1 neutron, whereas the tritium nucleus has 1 proton and 2 neutrons respectively. However, all isotopes of an element have the same number of protons and electrons. Since the chemical properties of an element depend upon the electronic structure, isotopes have identical chemical properties. Other than isotopes, there are isobars and isotones also. Isobars are nuclides of different elements having the same number of nucleons or the same atomic mass number, A. For example, tritium and helium-3 are different elements with the same mass number and hence can be termed as isobars. Isotones are nuclides of different elements having equal number of neutrons but different atomic numbers, Z. For example, silicon-30 and phosphorus-31 are example for isotones since both these nuclides contain 16 neutrons, as is evident from their notation. Until now, we have discussed about the constituents of the nucleus and different types of nuclides. Let us now look at the size of a nucleus. In an experiment suggested by Rutherford to his students, a gold foil was bombarded with alpha particles of kinetic energy 5.5 MeV. It was observed that the distance of closest approach of the alpha particle to the gold foil was 4 × 10⁻⁻15 meters. The scattering in Rutherford's experiment was assumed to be purely due to Coulomb's repulsion. As the positive charge of the atom is confined to the nucleus, the size of the nucleus had to be less than 4.0 × 10⁻⁻14 meter. Rutherford's calculations were based purely on the repulsive forces existing between the positively charged alpha particles and the gold nuclei. If alpha particles of kinetic energy higher than 5.5 MeV are used, then the distance of closest approach will be much lesser. But at some distance, the scattering would then be affected by the short-range attractive nuclear forces and hence they will deviate from the values obtained by Rutherford. It was found that a nucleus of atomic mass number A has a radius r, which is equal to r naught into a power 1 by 3, where r naught, a constant, is equal to 1.2 into 10 power minus 15 meter. Compared to an atom, the nucleus is very small, nearly 10 power 4 times smaller than an atom. Therefore, the nuclear volume is proportional to r cube and r is proportional to a power 1 by 3. This implies volume is proportional to the atomic mass number, that is, proportional to the number of nucleons. The nuclear density is constant and is independent of the mass number A. We can imagine nuclei of various elements as liquid drops of constant density. The density of nuclear matter is 2.3 into 10 power 17 kilogram per meter cube. This is because of the fact that all matter, including water, is made up of atoms, and atoms are almost empty except for a very small nucleus. In nature, we come across many elements. Some of them have nuclei which are highly stable, while others are relatively less stable. For example, the nucleus of iron is very stable, while the nucleus of uranium is considered to be unstable. To understand this aspect of nuclear stability, we should first study about Einstein's mass-energy equivalence relation. According to Einstein's mass-energy equivalence relation, energy and mass are equivalent to each other, and one can be converted into the other. When a certain mass m is destroyed completely, the amount of the energy released is given by Einstein's mass-energy equivalence relation as E is equal to mc square, where c is the velocity of light, which is equal to 3 into 10 power 8 meter per second. Here, E is referred to as the energy equivalent of the mass. According to Einstein, mass is a form of energy and it can be converted into other forms of energy, say kinetic energy, and vice versa. Let us now look at how much energy is released when one atomic mass unit of mass is completely destroyed. We know that the energy E released during this process is given by E is equal to mc square. Substituting mass m as 1 AMU, which is equal to 1.66 into 10 power minus 27 kilogram. Speed of light c equal to 3 into 10 power 8 meter per second, and simplifying, we get E is equal to 1.4924 into 10 power minus 10 joule, which can also be expressed as 931.5 million electron volt. Let this be equation 1. For a mass of 1 AMU, the energy equivalent is 931.5 million electron volt. For any mass m equal to delta m, the energy equivalent is given by E equal to delta m into 931.5 MeV. Therefore, we can say that 1 AMU mass is equal to 931.5 MeV by c square. This is an enormous amount of energy release. Let us now study the concept of nuclear binding energy in light of Einstein's mass-energy equivalence equation. Considering a sample nucleus, say, an oxygen nucleus. An oxygen nucleus is made up of 8 neutrons and 8 protons, and hence its atomic number Z equals to 8 and mass number A is equal to 16. The mass of each proton is Mp is equal to 1.00727 AMU. The mass of each neutron is Mn equal to 1.00866 AMU. And that of an electron is Me equal to 0.00055 AMU. The total mass of the constituents of the oxygen nucleus is the sum of the masses of 8 protons and 8 neutrons put together, and this is equal to 16.12744 AMU. Theoretically, this is the expected mass of the oxygen nucleus. But the actual mass of the oxygen atom M, determined experimentally using the mass spectroscopy principles, is 15.99493 AMU. When the mass of the 8 electrons is deducted from this, we get the mass of the oxygen nucleus as 15.99053 AMU. Hence, we observe that there is a difference between the theoretically expected mass of the nucleus and the actual mass of the nucleus, which was determined experimentally, and this difference is observed to be 0.13691 AMU. This difference between the theoretically expected mass of the nucleus and the actual mass of the nucleus is called the mass defect, denoted by delta M. Mass defect delta M for a nucleus can be determined by equation 2 as shown, where Z is the atomic number of the element, A is the mass number, A minus Z denotes the number of the neutrons in the nucleus. Mn is the mass of each neutron. Mp is the mass of each proton, and M dash denotes the actual mass of the nucleus. Equation 2 can also be written as MTH minus M dash, where MTH is the theoretical mass of nucleus, which is equal to Z into Mp plus A minus Z into Mn. Since the mass of the nucleus is less than the sum of the masses of its constituents, there exists a mass defect. Hence, the equivalent energy of the nucleus is less than that of the sum of the equivalent energies of its constituents. If an oxygen nucleus has to be broken up into its constituent protons and neutrons, energy equivalent to the mass defect needs to be supplied. The energy equivalent to the mass defect is obtained by the Einstein's mass-energy relation. This energy is called the binding energy and is denoted by EB is equal to delta M into C square, if delta M is taken in kilogram. If delta M is taken in million electron volt, then EB is equal to delta M into 931.5 as discussed earlier. Energy equal to binding energy is released when the constituents of a nucleus are brought together. This same energy is required to break a nucleus into its constituent nucleons. For the oxygen nucleus, substituting the values of mass defect delta M equal to 0.13691 AMU and simplifying, we get EB is equal to 127.5 MeV. The value of EB can be obtained in Joule if we take delta M in kilogram. The ratio of the binding energy to the mass number A of the nucleus is called as the binding energy per nucleon or average binding energy and is denoted by EBN. EBN is equal to EB by A. Average binding energy is the energy required to remove a nucleon from the nucleus. For the oxygen nucleus, the average binding energy is equal to 7.96875 MeV per nucleon. Average binding energy of various nuclei indicates the relative stability of the nuclei. High average binding energy values indicate highly stable nuclei, while low average binding energy values indicate low stability for the nucleus. We can understand the relative stability of the various nuclei of the elements by plotting a graph between the average binding energy values on the y-axis and the corresponding mass number values on the x-axis. From the graph, we see that for nuclei with mass numbers less than 30, the average binding energy values are relatively less, indicating relatively low stability for those nuclei. The average binding energy is almost independent of the mass number A of nuclei in the range of mass numbers between 30 and 170 and is nearer to the maximum value of the average binding energy. This indicates high stability for the corresponding nuclei. The average binding energy is maximum for a nucleus of iron of mass number A equal to 56 and is equal to 8.75 MeV. We also see that the average binding energy has a value of 7.6 MeV for A is equal to 238. It is observed that the binding energy per nucleon is lower for both light and heavy nuclei. That is, for nuclei with mass number A less than 30 and greater than 170. From the observations of the graph, a few conclusions can be drawn regarding the type of forces that exist between the nucleons in the nucleus. To produce a binding energy of a few MeV per nucleon, the force between the nucleons should be attractive and sufficiently strong. The constancy of the binding energy in the range where mass number A varies from 30 to 170 shows that the nuclear forces are short-ranged. A nucleon will be under the influence of some of its neighbors, which come within the range of the nuclear force. If any other nucleon is at a distance more than the range of the nuclear force from the particular nucleon, then it will have no influence on the binding energy of the nucleon under consideration. If a nucleon can have P neighbor within the range of the nuclear force, then its average binding energy will be proportionally to P and hence can be written as pK, where K is a constant having the dimensions of energy. If nucleons are added to the nucleus to increase its mass number A, there would be very little change in the average binding energy of each nucleon, as most of the nucleons inside a large nucleus reside well inside the nucleus and not on the surface. Hence, the average binding energy remains constant and is approximately equal to pK. The property that a given nucleon is influenced only by nucleons close to it is referred to as the saturation property of the nuclear force. This is observed in large or medium-sized nuclei. A very heavy nucleus, say A is equal to 240, has lower binding energy per nucleon compared to that of a nucleus with A is equal to 120. Thus, if a nucleus A is equal to 240 breaks into two, A is equal to 120 nuclei, in a process called the nuclear fission. The nuclei get more tightly bound and hence become more stable in the process. This shows that a large amount of energy would be released in this process. This is the reason for the high energy release in nuclear fission. Similar is the situation when two very light nuclei with A around 10 join to form a heavier nucleus by a process called the nuclear fusion. The binding energy per nucleon of the fused heavier nucleus is more than the binding energy per nucleon of the lighter nuclei. This means that the final system is more tightly bound than the initial system. Again, energy would be released in such a fusion process. Thus, we observe that for most of the nuclei, the binding energy per nucleon is very large compared to the binding energy of atoms in a molecule. Thus, there should be a strong attractive force among the nucleons in the nucleus, which can bind the nucleons together in the tiny nuclear volume in spite of the Coulomb repulsive forces that exist between the positively charged protons. This force is called the nuclear force. From our analysis of the nuclei, we come to know some features of nuclear force. Nuclear force has to overcome the Coulomb force between protons and keep them together. So, nuclear force must be stronger than Coulomb force. As gravitational force is weaker than Coulomb force, we can conclude that nuclear force is stronger than both Coulomb and gravitational force. Therefore, nuclear forces are the strongest forces in nature. This can be observed from a graph of nuclear force versus distance between nucleons. Here is the graph showing a plot of potential energy between a pair of nucleons against their separation. It is observed that potential energy is the least for a distance r0 of about 0.8 Fermi. From the graph, we see that the potential energy is very high for r values less than 0.8 Fermi, which implies that the nuclear forces are very strong in that range. This force falls rapidly to zero as R value crosses 0.8 Fermi. Nuclear forces bind the nucleons together. That is, they exist between two protons, two neutrons, and also a proton and a neutron. Therefore, nuclear forces are independent of the charge and the nuclear force acting between two neutrons, or between two protons, or between a neutron and proton, is approximately equal in magnitude. We have simple mathematical equations representing the Coulomb force and the gravitational force, but we do not have any such mathematical expression for the nuclear force. The study of radioactivity has shown that a radioactive nucleus disintegrates or decays spontaneously. During a radioactive decay process, the original nucleus is referred to as parent nucleus, and the residual or resultant nucleus is referred to as the daughter nucleus. In nature, a radioactive nucleus can decay by three modes, namely alpha decay, beta decay, and gamma decay. Let us first study alpha decay. An alpha particle is a helium nucleus containing two protons and two neutrons. That is, its mass number is 4 and atomic number is 2. Since an alpha particle is a helium nucleus, when an unstable nucleus emits an alpha particle, its neutron number as well as proton number reduce by 2. Therefore, when a nucleus decays by emission of an alpha particle, the mass number A of the daughter nucleus reduces by 4 and the atomic number Z reduces by 2. Since the proton number Z of the nucleus changes in this decay process, the chemical symbol of the daughter nucleus is different from that of the parent nucleus. If a radioactive nucleus X having an atomic number Z and mass number A emits an alpha particle, then it transforms into a nucleus Y with atomic number Z-2 and mass number A-4. Let this be equation 1. The heavy nucleus emits an alpha particle, thereby reduces its mass and hence moves towards stability. Alpha decay occurs in all nuclei with mass number A greater than 210. For example, americium-241 undergoes alpha decay to form neptunium-237. Americium-241 with atomic number 95 emits an alpha particle and decays to neptunium-237 with atomic number 93. The total mass of the decay products, that is neptunium-237 and helium-4, is less than that of the parent nucleus, americium-241. Hence, the total mass energy of the decay products is less than the mass energy of the original nuclide. Therefore, alpha decay is a spontaneous decay without the need of any external source. The difference between the rest mass energy of the initial constituents and that of the final products is called the Q value of the reaction. If Ui denotes the rest mass energy of the initial constituents and UF denotes the rest mass energy of the final products, then the Q value for the reaction will be equal to Ui minus UF. Let this be equation 2. This definition of the Q value is valid not only for alpha decay, but in general to all nuclear processes. Q denotes the energy made available as kinetic energy of the products. Thus, the Q value of an alpha decay can be expressed as Q is equal to mx minus my minus mhe into c square. Here, mx is the mass of parent nucleus, my is the mass of daughter nucleus, and mhe is the mass of a helium nucleus, and c is the velocity of light. Let this be equation 3. Thus, the disintegration energy, Q, is shared by the daughter nucleus and the helium nucleus in the form of kinetic energy. Alpha decay obeys both the laws of radioactive decay, that is, N is equal to N naught into e power minus lambda T, and R is equal to R naught into e power minus lambda T, where lambda is the decay constant. Now let us study beta decay. In beta decay, a nucleus decays spontaneously by the emission of an electron or a positron. In a beta decay process, a neutron converts into a proton or a proton converts into a neutron. If N denotes the neutron number of the nucleus and Z is the proton number, then N by Z is altered in a beta decay process. If the nucleus is formed with more number of neutrons than the number needed for stability, then a neutron will convert itself into a proton. If a nucleus is formed with more number of protons than needed for stability, then a proton will convert itself into a neutron. Such transformations take place because of weak forces within the proton or the neutron. the decay in which an electron is emitted is called beta minus decay. In this decay, a neutral, massless particle called an antineutrino, denoted by the symbol nu bar, is also emitted. For example, when carbon-14 decays into nitrogen-14, it emits an electron and an antineutrino, which is denoted by nu bar. This is called beta minus decay, since the particle emitted is the electron. Here, we see that a neutron converts into a proton and in the process emits an electron. In beta minus decay, the atomic number of the daughter nucleus is 1 more than the atomic number of the parent nucleus, with their mass numbers being the same. In beta minus decay, a neutron transforms into a proton within the nucleus. Along with this transformation, an electron and an antineutrino are also emitted. Let us now calculate the Q value for the beta minus decay. The rest mass energy of the initial constituents is equal to Ui, given by equation 4. The rest mass energy of the final products is equal to Uf, given by equation 5. Then, the Q value of the reaction will be Ui minus Uf. The Q value can be obtained by substituting the values of Ui and Uf. Let this be equation 6. Because of the large mass, the daughter nucleus formed does not share an appreciable part of the kinetic energy. Thus, the energy Q is shared by the antineutrino and the beta particle. Now let us study beta plus decay. The decay in which a positron is emitted is called beta plus decay. In this decay, a neutral, massless particle called a neutrino is also emitted. A neutrino is denoted by nu. For example, when carbon-10 decays into boron-10, it emits a positron and a neutrino. This is called beta plus decay, since the particle emitted is the positron. In a beta plus decay, the atomic number of the daughter nucleus is 1 less than the atomic number of the parent nucleus, with their mass numbers being the same. In beta plus decay, a proton transforms into a neutron inside the nucleus. Along with this transformation, a positron and a neutrino are also emitted. Let us now calculate the Q value for beta plus decay. The rest mass energy of the initial constituents is equal to Ui, given by equation 7. The rest mass energy of the final products is equal to Uf, given by equation 8. Then, the Q value of the reaction will be Ui minus Uf, as given by equation 9. We observe that in a beta decay process, when one nucleon transforms into another nucleon, there is no change in the mass number. Beta decay also follows the 2 laws of radioactive decay. Here, it is important to note that neutrinos interact very weakly with matter. Neutrinos can even pass through the earth without being absorbed and hence are very difficult to detect. Now, let us study gamma decay. In gamma decay, high-energy photons are emitted. Here, there is only a change in energy of the nucleus, but no change in its composition. Usually, an alpha decay or beta decay leaves the daughter nucleus in an excited state. The daughter nucleus reaches the ground state by a single transition or sometimes by successive transitions emitting one or more gamma rays, that is, by gamma decay. For example, a cobalt-60 nucleus transforms into nickel-60 by beta-minus decay. This nickel-60 nucleus is an excited state and comes to its ground state by successive emission of 1.17 MeV and 1.33 MeV gamma rays. To summarize, an unstable nucleus undergoes radioactive decay to attain stability. In alpha decay process, a radioactive nucleus emits an alpha particle, which is a helium nucleus. Here, the mass number A and atomic number Z are altered. In beta decay process, a radioactive nucleus emits a beta particle, which is an electron or a positron. Here, the atomic number Z is altered. In gamma decay process, a nucleus in an excited state emits a high-energy photon to reach a lower energy state. Here, only the energy levels change and there is no change in either the mass number A or the atomic number Z. Radioactivity is a phenomenon which is exhibited by elements with unstable nuclei. It was accidentally discovered by Henry Becquerel in 1896. While studying the phenomena of fluorescence and phosphorescence, Becquerel came across a mineral which shone in bright sunlight. But when the weather became cloudy, its fluorescence ceased. As the weather remained cloudy, he wrapped the mineral sample in black paper, put the contents in a closed desk, and forgot about it. Incidentally, the mineral happened to be placed over a Maltese cross, which was kept over a light-proof box of unexposed photographic film. Some days later, when Becquerel took the mineral out, he noticed that the photographic film appeared fogged. Becquerel reasoned that the material emitted fluorescence even in absence of sunlight. When the photographic film was developed, Becquerel found that the film was fogged with an image of the Maltese cross. This is how the photographic film looked after it was developed. Becquerel assumed that the fogging of the film was due to some rays emitted from the mineral compound, which could penetrate through the black paper and the silver cross and expose onto the photographic film. On further studies, it was found that the mineral Becquerel used in his experiment contained uranium salts, and that uranium emitted radiation constantly without any excitation or charge by an external source. Later studies and experiments based on these observations conclusively proved that this was a nuclear phenomenon known as radioactivity exhibited by some elements having unstable nuclei. Unstable nuclei can attain stability by emitting particles. A nuclear phenomenon in which an unstable nucleus undergoes decay is called radioactive decay. In nature, a radioactive nucleus can decay by three modes, namely the alpha decay, the beta decay, and the gamma decay. In alpha decay, a radioactive nucleus emits a helium nucleus, which is referred to as an alpha particle. In beta decay, a radioactive nucleus emits either an electron or a positron. A positron is a positively charged particle with mass same as that of an electron and magnitude of charge also exactly same as that on an electron. If an unstable nucleus releases an electron along with an antineutrino, it undergoes a beta minus decay. If it releases a positron along with a neutrino, it undergoes a beta plus decay. In gamma decay, the radioactive nucleus emits high-energy photon. A detailed study of alpha decay, beta decay, and gamma decay will be taken up later. Let us first derive a relation for the rate of radioactive decay. For this, let us consider a sample of a radioactive element containing n number of radioactive atoms at time t. The number of nuclei, dn, which will decay, will be proportional to n, since the more the n value, more will decay in the time interval dt. The number of nuclei that will decay will also be proportional to the time interval dt. If we take a longer dt into consideration, then more nuclei will decay in this longer interval dt, since longer the interval, greater the chance of decaying. Thus, dn will be proportional to n dt. Or we can say dn will be equal to minus lambda n dt. Here, lambda is a constant of proportionality and is called the decay constant or disintegration constant. Negative sign shows decay of nuclei. This implies that dn by dt is equal to minus lambda n. Let this be equation 1. This can also be written as dn by n is equal to minus lambda dt. Let this be equation 2. Integrating equation 2, we get integral dn by n in the limits n naught to n is equal to minus lambda integral dt in the limits t naught to t. Here, n naught is the initial number of nuclei at time t naught, and n is the number of nuclei at a later time t. Evaluating the integral, we get log n to the base e minus log n naught to the base e is equal to minus lambda t minus t naught. If we take the initial time t naught as 0, we get log n by n naught to the base e is equal to minus lambda t. This can also be written as n is equal to n naught e to the power of minus lambda t. This equation is called the law of radioactive decay. Let this be equation 3. In general, we are interested in the number of nuclei decaying per unit time than the number of nuclei present in the sample. Number of nuclei decaying per unit time is known as the decay rate and is denoted by R. R is equal to minus dn by dt. Let this be equation 4. Decay rate R is also called the activity A of the sample. Substituting equation 3 in the equation 4, we get R is equal to minus d by dt of n naught into e power minus lambda t. Simplifying further, we get R is equal to lambda n naught e power minus lambda t. Let this be equation 5. Substituting equation 3 in equation 5, we get R is equal to lambda n. Now, at time t is equal to 0, let R be equal to R naught. Then, R naught can be written as R naught is equal to lambda into N naught. Substituting R naught in the place of lambda N naught in equation 5, we get R is equal to R naught e power minus lambda t. This is another form of the law of radioactive decay. Let this be equation 6. The SI unit for decay rate R is becquerel, denoted by BQ as shown. 1 becquerel is equal to 1 decay per second. Another unit of R is curie, denoted by Ci as shown. 1 curie is equal to 3.7 into 10 power 10 becquerel. The period of time taken by a substance undergoing decay to decrease by half is known as half-life period. It is the time interval for which both N and R are reduced to half of their initial values. Half-life period is denoted by T half. From equation 6, we have R is equal to R naught into e power minus lambda t. Substituting R equal to R naught by 2 and T equal to T half in equation 6 and solving, we get T half is equal to log 2 to the base E by lambda. Substituting the value of log 2, we get T half is equal to 0.693 by lambda. Let this be equation 7. Another measure of estimating the time for which a radioactive nuclei lasts is the mean life or average life, denoted by tau. It is the average time a substance exists in a specified form. It is the time interval in which N and R reduces to 1 by E of its original value. Let us now substitute R equal to R naught by E and T equal to tau in equation 6. We get R naught by E is equal to R naught into e power minus lambda tau. On simplifying, we get tau is equal to 1 by lambda. It shows that mean life tau is the reciprocal of the disintegration constant. Now, T half is equal to 0.693 tau. It is important to note that these relations for half-life and mean life are statistical in nature. They cannot predict the exact behavior of each and every nucleus in the radioactive sample considered. Rather, they only predict the total numbers. For example, consider a sample of 100 atoms of radioactive nuclide of half-life 20 hours. Since the half-life is 20 hours, we can say that 50 atoms of the radioactive sample would decay in 20 hours. But we cannot predict exactly which particular 50 atoms of the sample would decay. Experiments have proved that even though the sample contains all similar nuclei, under identical conditions, all of them may not decay simultaneously. Thus, it is impossible to predict when a particular nucleus will decay. However, prediction can be made about how many of these nuclei will decay in the small interval of time dt. Therefore, the equations developed for radioactive decay will work only when n is large. Previously, you have learnt about alpha, beta, and gamma emissions by relatively. From the curve showing the variation in average binding energy versus the mass number A, we have seen that elements with A ranging from 30 to 170, like iron, cobalt, etc., have relatively high binding energy per nucleon, EBN, and of nearly 8 MeV. The nuclei with average binding energy of approximately. From the same curve, we observe that the nuclei with mass number less than 30 and greater than 170 have binding energy per nucleon. This implies that when tightly bound nuclei transform into relatively less tightly bound nuclei, when such nuclear transformations occur, an enormous amount of nuclear energy is released, as in the case of nuclear fission or nuclear fusion, which you will learn in detail later. Let us now compare this energy to that which is released when we use conventional energy resources like coal, petroleum, etc. Conventional energy resources release energy through chemical reactions. For example, when 1 kilogram of coal is burnt, the amount of energy released is about 10 to the power 7 joule. But the nuclear energy released in the fission of 1 kilogram of uranium is about 10 to the power 14 joule, which is a million times greater than that released by a conventional source of energy. Therefore, the energy obtained from a nuclear source is considerably enormous compared to that obtained from an equivalent mass of conventional source of energy. At the same time, we have to remember that since a large amount of radiation is involved in such nuclear processes, they are extremely hazardous if not handled carefully. Let us now look at the nuclear processes which release such enormous amounts of nuclear energy. An Italian-American physicist, Enrico Fermi, found that when neutrons are bombarded onto various elements, new radioactive elements may be produced. For example, when cobalt-59 is bombarded with neutrons, it captures a neutron and transforms to cobalt-60, which is radioactive in nature. But when a uranium target is bombarded with a neutron, it splits into two almost equal fragments, accompanied by the release of a large amount of energy. This nuclear process is called nuclear fission. Let us look at an example of nuclear fission. When uranium-235 absorbs a neutron, it becomes unstable and undergoes nuclear fission. The fission products are barium-144, krypton-89, and 3 neutrons. It is also observed that in such type of fission, the products need not always be barium and krypton. The fission products of uranium-235 can also be antimony-133, niobium-99, and 4 neutrons, or xenon-140, strontium-94, and 2 neutrons. Thus, we see that nuclear fission involves the release of neutrons along with other products which may vary. We also see that the number of neutrons released also varies depending on the other products of fission being released. Let us now estimate the amount of nuclear energy or the value of Q being released during fission. Consider a nucleus of mass number A equal to 240 undergoing a nuclear fission. From the average binding energy versus mass number curve, we observe that for A equal to 240, the average binding energy is 7.6 MeV. Therefore, the total binding energy for this nuclide is 240 into 7.6, which is equal to 1824 MeV. Let us now assume that this nucleus undergoes nuclear fission and forms into two fragments with atomic mass number A equal to 120 each. From the graph, we find that for nuclei with A equal to 120, average binding energy is about 8.5 MeV. So, the total binding energy for the product nuclides is equal to 2 into 120 into 8.5, that is 2040 MeV for the two products put together. This shows that when a single nucleus of mass number 240 splits into two nuclei, the gain in binding energy is 2040 minus 1824, which is equal to 216 MeV. This energy is extremely large and is about 1 million times larger than the conventional energy sources like wood, coal, petroleum, etc. The enormous amount of energy, which is the disintegration energy of the fission process, initially appears as the kinetic energy of the fission products and the neutrons, and finally is transferred as heat into the surrounding matter. Thus, a nuclear fission process generates an enormous amount of heat energy. It is also observed that nuclear fission products are highly rich in neutrons and are unstable and radioactive. They emit beta particles in succession until they reach a stable end product. Put to proper use, this nuclear energy can be used to generate electricity in a nuclear power plant. On the other hand, high levels of energy and radiation in an atomic bomb can be obtained by an uncontrolled nuclear fission, causing grave damage to nature and mankind. Thus, the same fission reaction is the base for the useful nuclear reactor as well as the destructive atomic bombs. It depends on us how we use it. We know that when a uranium-235 nucleus absorbs a neutron, it undergoes fission and in the process releases neutrons. Nuclear fission of a heavy nucleus like uranium-235 yields enormous amount of energy. Also, 3 neutrons are released along with the fission products. In fact, an average of 2.5 neutrons are released in the fission of a uranium nucleus. We know that along with the fission products, say barium-144 and krypton-89, 3 neutrons are released during its fission. However, if these neutrons are absorbed by 3 other uranium nuclei, it can cause fission in them. Each uranium nucleus thus undergoes fission. Their fission results in the release of a total of 9 neutrons, which can cause further fission in 9 other uranium nuclei. In this manner, a chain of uranium fission reactions take place in a very short interval of time, thereby releasing an enormous amount of energy. This is called a chain reaction. It was first suggested by Enrico Fermi. A chain reaction is one in which the fission of a uranium nucleus, once initiated with the absorption of external neutrons, occurs rapidly without the aid of external neutrons. If a chain reaction is not controlled, it can be highly hazardous as it releases an enormous amount of energy that can cause harm to human beings and the environment to a large extent. The explosion of an atom bomb is an example of a chain reaction. It explodes due to the uncontrolled chain reaction of fissionable materials. If a chain reaction is controlled, we can harness an enormous amount of energy it releases for peaceful purposes such as generate electricity in a nuclear reactor. A nuclear reactor is a device in which a steadily controlled fission reaction takes place. Let us now study about the design and working of a nuclear reactor with uranium as the fissionable material. Uranium is taken in the form of cylindrical rods. These rods are arranged in a regular pattern within the active reactor core. The volume of the core is filled with a light nuclei material like either water, heavy water or graphite, which are called moderators. The neutrons released during the fission of uranium-235 have kinetic energies of approximately 2 million electron volt and are called fast neutrons. These fast neutrons escape from the uranium and enter the moderator. It is observed that the probability of uranium-235 undergoing fission is high when it absorbs neutrons with energies of approximately 0.04 electron volt that are typically called the slow neutrons. The probability of absorption of fast neutrons by uranium-235 is very low, and hence it does not help in the fission of uranium-235. The fast neutrons can be slowed down, that is, converted into slow neutrons by means of elastic scattering with light nuclei to sustain the fission reaction of other uranium nuclei. These light nuclei material called the moderator, which provided along with the fissionable material, slow down the neutrons released during fission and therefore help to increase the probability of fission of uranium-235 nuclei. Thus, the function of a moderator is to slow down the neutrons released during fission so that they can be absorbed by further uranium nuclei. In a pressurized water reactor, water is used as a moderator as well as a coolant to absorb the enormous amount of energy released in the reactor. The geometry of the core is such that out of an average of 2.5 neutrons released per fission, 1 neutron triggers the next fission reaction and the remaining ones are lost without causing further fission. That is, they are absorbed by the control rods. Control rods are used to control the rate of the fission reaction. Control rods are made of materials like cadmium. Cadmium is a very good neutron absorber, and it can be inserted into the moderator at a certain depth. Thus, the fission reaction can be sustained at a constant rate. Let us now define a quantity called the multiplication factor K for a reactor, which is a measure of the growth rate of the neutrons in the reactor. Multiplication factor K is defined as the ratio of the number of fissions produced by a specific generation of neutrons to the number of fissions produced by the previous neutron generation. As previously mentioned, out of an average of 2.5 neutrons produced, fission is always caused by 1 neutron only, and the value of K is equal to 1. This state is called the critical state of the reactor, wherein the reaction runs at a constant rate. If the cadmium rods maintaining the critical state are now drawn out of the reactor, then more number of neutrons will be available for further fission and the multiplication factor K becomes greater than 1. Thus, the fission rate increases rapidly and leads to an explosion. Again, consider the case when the reactor is just critical. If the cadmium rods are now pushed further into the moderator, they absorb more neutrons than earlier. The number of neutrons available for further fission becomes less. This reduces the multiplication factor K to less than 1. In such a case, the rate of fission decreases and the reactor shuts off. Thus, the control rods regulate the fission rate. In addition to the control rods, additional rods called the safety rods are provided in the reactor. Whenever required, these rods can be inserted into the reactor and can rapidly bring down the value of the multiplication factor K to less than 1. In the reactor core, a lot of energy in the form of heat is released, which can be utilized for the generation of electricity. Water at high pressure or molten sodium is passed through the reactor core to withdraw the heat produced in the core. The material that is used to extract the heat out of the core of a nuclear reactor is called the coolant. Nuclear fission and nuclear fusion are two nuclear processes that release enormous amounts of energy. You have already learned about nuclear fission. It is a process in which a heavier nucleus splits into two lighter nuclei with the release of a large amount of energy. Now, you will study about nuclear fusion. In the nuclear fusion process, two lighter nuclei combine to form a heavier nucleus, releasing a large amount of energy. For example, when two hydrogen nuclei, that is, protons, fuse together, a larger nucleus of deuterium is formed. In this process, a large amount of energy, approximately equal to 0.42 million electron volt, is released. Similarly, when two nuclei of deuterium fuse together to form a nucleus of helium, energy equal to 3.27 million electron volt is released in the process along with a neutron. Two nuclei of deuterium can also fuse together to form a nucleus of tritium, releasing an energy equal to 4.03 MeV along with a proton. In all these nuclear fusion processes, we see that two nuclei combine to form a heavier nucleus. We know that the nuclei are positively charged, and as such, the nuclear fusion process occurs only when the nuclei overcome the Coulomb's repulsive force between them and come close enough to be within the range of the attractive nuclear forces between them. The Coulomb's repulsive force is referred to as the Coulomb barrier, and the height of this barrier depends on the charges and also on the radii of the two fusing nuclei. If two protons, that is, two hydrogen nuclei, should fuse together, the barrier height is about 400 kilo-electron volt. This is a very huge amount of energy. To overcome the Coulomb barrier, the required energy is obtained thermally, that is, by raising the temperature of the proton gas. Let the temperature of the protons be raised to T to obtain energy of 400 kilo-electron volt. We know that the energy gained must be equal to 3 by 2 kT, where K is the Boltzmann's constant. Substituting the value of the Boltzmann constant and simplifying, we get temperature T equal to 3 into 10 power 9 Kelvin. Therefore, the temperature of the protons has to be raised to this value, so as to enable them to overcome the Coulomb barrier by thermal motion alone. This process is called thermonuclear fusion. Let us now consider the Sun's core, which is at temperature of about 1.5 into 10 power 7 Kelvin. But it is observed that protons fuse together in the Sun, even though the temperature is 100 times lesser than what is required for the protons to fuse. The reason for this puzzle lies in the fact that 3 by 2 kT represents the average kinetic energy of the molecules. But then, there are some nuclei which have kinetic energy more than the average values, and such nuclei overcome the Coulomb barrier. Therefore, we see that the Sun's core has extreme conditions of high temperature and high pressure to enable the nuclei to fuse together. Such thermonuclear fusion reactions occur in the Sun and other stars and form the source of the enormous amount of energy of the stars. We know the Sun has been a source of energy for us over the past 5 into 10 power 9 years, and estimates show that this can continue for the next 5 billion years. Obviously, the fusion reaction taking place in a repetitive cycle forms the source for such continuous energy generation. In the nuclear fusion process taking place in the Sun, hydrogen nuclei fuse together to form the heavier helium nucleus and in the process release enormous amount of energy. This is a multi-step process and is called the proton-proton cycle of nuclear reactions. In the first step of the proton-proton cycle, 2 hydrogen nuclei fuse together to form a deuteron releasing a positron and a neutrino along with energy. The deuteron formed in the first step fuses with another hydrogen nucleus to form a lighter helium-3 nucleus releasing gamma rays. In the last step of the process, the helium-3 nucleus combines with another helium-3 nucleus to form a stable helium-4 nucleus along with 2 hydrogen nuclei releasing energy in the process. For the last step to occur, the processes represented by equations 1, 2 must occur twice. The net effect of the above multiple step process is that 4 hydrogen nuclei fuse together to form a helium nucleus releasing 2 positrons and gamma particles along with energy equal to 26.7 million electron volt. This process is estimated to run in the Sun's core for about 5 billion more years, by which it would mostly contain helium nuclei. Then, the Sun's core will begin to cool down and the Sun will collapse under its own gravity. In this phase, the Sun will be called the red giant. If the temperature of the Sun rises again to 10 power 8 Kelvin, then helium nuclei can fuse to form carbon. As the star evolves further and becomes hotter and hotter, other elements with more number of protons can be formed. But we must note that the elements more massive than those which are near the peaks of the binding energy curve cannot be formed by further fusion. The first thermonuclear fusion reaction occurred on the Earth by the explosion of a nuclear fusion device, and energy equal to about 2.6 into 10 power 29 million electron volt was produced in the process. It occurred at Nuclei Atoll, a part of Marshall Islands in North Pacific. However, we must note that a sustained and controllable source of nuclear fusion power is difficult to achieve on the Earth due to the inherent difficulties involved, like conditions existing in stars.